Okay, so this is the solutions for assignment 11. Number 1, a large water wheel of radius 0.9 meters is spinning with an angular velocity of 6 radians per second. A constant angular acceleration acts on the wheel for 8 seconds, and its final angular velocity is 18 radians per second. Find the angular acceleration. So, for angular acceleration, we have that it is equal to delta omega over delta t, and our final minus our initial angular velocities over the time it takes to make the change is going to be equal to an alpha of 1.5 radians per second. Seconds squared. Almost forgot my unit there. B, find the angular displacement of the water wheel over 8 seconds using a constant angular acceleration equation. I am going to use this one here, where I'm using theta is equal to the initial omega times time plus 1/2 the alpha we just found times the time squared. Plugging in, that is going to give us 6 times 8 plus 1/2 times 1.5 times 8 squared. And that gives us a theta of 96 radians. Part C. What is the tangential speed of a point on the outer surface of the water wheel after the 8 seconds? So, tangential velocity is equal to r times omega, which is 0.9, times the 18, because this is after the 8 seconds. So the tangential velocity is equal to 16.2 meters per second. Part D, what is the radial acceleration of the same point on the outer surface? Radial acceleration is equal to r times omega squared, which is again the 0.9 times the 18, but instead it is squared this time. And our radial acceleration is 291.6 meters per second squared. Oh, that was question 1. Question 2. A car's steering wheel is mounted horizontally, and it is modeled by a uniform disc of mass 5 kilograms and radius 0.25 meters. It can freely rotate around the central axis. You grip the wheel on opposite sides and push forwards with one hand, while you pull backwards with the other. Typo. Both with a force of 15 newtons. So these are your hands applying a force. There's a small frictional torque from the steering column of 2.5 newton meters, or meters times newtons. The wheel starts from rest. Find the moment of inertia of the wheel. So we are told it is a cylinder, or a uniform disc, actually I should say, my bad. And the formula for that is 1/2 mr squared. So plugging in some values, I got 5 for the mass and 0.25 for the radius. My moment of inertia is 0.15625 kilogram meter squared. I'm leaving a bunch of decimal places because I know I will be needing that number later on. Find the net torque on the wheel. So net torque is going to be equal to the torque of the right hand plus the torque of the left hand plus the torque due to friction. The torque of the right hand is going to be RF plus the RF from the left hand minus the 2.5 torque that we are told friction generates. So the reason friction is negative and the other two torques from both your hands are both positive is because your hands are both generating a torque that is counterclockwise, which we defined as positive in class, and friction generates a torque that is clockwise, which we defined as negative in class. So That's why I have both the left and right-handed torques as positive and the friction as negative. The two torques from both your hands are identical, so I'm going to say that this is 2 times 0.25 times 15 minus 2.5. That gives me 5 Newton meters of torque for the net torque. C, find the net force. 2 forces acting on the wheel. You have, from your right hand, 15 newtons up plus 15 newtons down from your left hand. That gives you a net force of 0 newtons. Find the angular acceleration of the wheel for part D here. So I know that torque is equal to I times alpha, so I know that alpha is equal to torque divided by I, and this is using the net torque, so 5 over the number I said I would put aside for earlier on, and this here gives me an alpha that is equal to 32 radians per second squared. E, if you maintain this torque until the wheel reaches an angular speed of 12 radians per second, how long will this take? So, rearranging one of our equations from the formula sheet, we get time is equal to omega over alpha. We are going to use the 12 radians we were just given, and the 32 we just calculated to get a time of 0.375 seconds. F, how much work did you do on the wheel over the time in part E? So here I get the work is equal to the torque that we produce, dotted with theta. Now this is the 7.5 torque. This is not 5. This is the work we do, so we are only considering the torque we exert. We are ignoring the 2.5 from friction. So if we take the net torque, add the 2.5 back, we exert a torque of 7.5 Newton meters, not 5. So this is not the net torque here. And I multiply that with theta. I don't know theta yet, so I'm going to use this formula. So omega F squared equals omega I squared plus 2 alpha theta. Omega I is gone. Theta is equal to omega F squared over 2 alpha, which is equal to 12 squared over 2 times 32, which gives me about 2.25 radians. Plugging that into my work equation here, I get a total work equal to 16.875 joules. Part G, calculate the power you exert on the wheel at 12 radians per second. So, power here is torque times omega. And again, this is the torque that you exert, not including friction. And at 12 radians per second, this gives you 90 watts. So power equals 90 watts. So that was for number 2. Number 3. 2 solid objects of identical mass and radius start from rest and roll without slipping from the same height of 2 meters down identical frictional ramps. One object is a solid disc while the other is a hoop. In all other aspects, they are identical. So I'm going to put disc over here on the left and the hoop on the right. I will start with the disc. I know that initially I have some gravitational potential energy, so I'll have mgh. And I know that at the bottom it will be translating and rotating So I'll have linear kinetic energy and rotational kinetic energy. I'm going to go ahead and do some substitutions here of my formulas. For the moment of inertia of a disk, I know that that is 1/2 mr squared. For omega, I know that is v over r. However, this is omega squared, so I square both things or everything inside the brackets. Here I have r above and below, so they cancel out. I have the same mass in every term, so they cancel out. I get GH equals 1/2 v squared plus 1/4 v squared here. I'm going to multiply everything by 2, get rid of one of the fractions. Makes the mental math easier for me here. This here is going to be 3 over 2 v squared. And isolating for v, I get the square root of 4 over 3 GH, which is equal to the square root of 4 over 3 times 9.8 times 2. And this gives me 5.112 meters per second. Now for the hoop, basically the same thing with a slightly different moment of inertia. Of just mr squared. Same idea, mass cancels, r squared cancels. I'm left with GH equals 1/2 v squared plus 1/2 v squared. I'm going to erase those 1/2s because they are awful and redraw them here. That looks a lot better. So GH equals v squared. V equals the square root of GH, which is the square root of 9.8 times 2. V equals 4.427 meters per second. So they both start from rest. So therefore, the disk reaches the bottom first. I know this because the velocity of the disk is greater than the velocity of the hoop. And I also know that because they start from rest, the acceleration, the linear acceleration of both, if I compare them, the disk will have a larger angular acceleration. So it will accelerate faster. It will reach the bottom first. They both start at the same place. They both go down the same ramp. They both start at rest. So the disk has to reach the bottom first. So now if they both continue onto a horizontal surface, which has the larger translational kinetic energy. So translational kinetic energy is just given by equals 1/2 mv squared. So for that, the masses, I'm told, are identical. They both have a factor of 1/2. So the only thing that matters is speed. So v squared there. So without even having to do the calculation, I know that the one with the larger speed, the disk, is going to have the larger translational kinetic energy. And it also asks which one will coast farther before coming to a rest if a small frictional force acts identically on both. So here, both of them have some translational kinetic energy and some rotational kinetic energy. We are told that there is no external torque, so there's nothing affecting the rotational kinetic energy. That is not going to determine how far it goes. We only have friction, which acts linearly on both the disk and the hoop. So the only thing we are really caring about here is the linear or translational kinetic energy. So therefore, the one with the larger translational kinetic energy will go farther. So that is the disk. So therefore, the disk goes farther. So that was question 3. Question 4. A block of mass 2 kilograms is attached to a light string wrapped around a uniform solid cylinder pulley of mass 1 kilogram and radius 0.1 meters. The block is released from rest and falls a distance of 1.5 meters, so the string unwinds without slipping and the pulley rotates. Ignore air resistance and the friction at the axle. Part A, find the speed of the falling block and the tangential speed of the pulley after the block has fallen 1.5 meters. So, the speed of the falling block and the tangential speed of the pulley. I'm also told that the string unwinds without slipping. Knowing this, that the string does not slip, speed of the falling block must be equal to the tangential speed of the pulley. So I'm going to use the same velocity v for both. Setting this equation up, I know that I have just some gravitational potential energy, mgh, initially. I know that the block will be moving while it falls at the end, and I know that the cylinder will be spinning. So I have translational kinetic energy and rotational kinetic energy of the block and the cylinder respectively. Doing some substitutions, I get mgh equals 1/2 mv squared plus 1/2 times the moment of inertia of a cylinder, which is the same as the disk, so that is mr squared. I'm using a big M here to tell me that it is not the same as little m. And omega is v over r, square everything in those brackets because omega is squared. I cannot cancel mass because big M is different than little m, and not everything has a little m or a big M, so I cannot cancel that. So here, I'm going to simplify a little bit. I have canceled out r squared, and I'm going to factor out v squared at the same time here. So v squared is equal to 1/2 m plus 1/4 big M. That means v is equal to the square root of mgh over 1/2 m plus 1/4 big M. Plugging in numbers, I get 2 times 9.8 times 1.5 on the top. On the bottom, I get 1/2 times 2 plus 1/4 times 1, not W, just V for velocity here. Plugging that all in, I get 4.849 meters per second. And again, that is the speed of the falling block and the tangential speed of the pulley. B, find the angular speed of the pulley when the block has fallen 1.5 meters. So that is omega equals v over r. And we're going to just take that value we just calculated with divided by the radius. And we get an omega of 48.49 radians per second. I didn't like that box. Cut off too much of the answer. Okay, see, what percentage of the lost gravitational potential energy has been transformed into rotational kinetic energy? So I'm going to first find my rotational kinetic energy here. That is 1/2 I omega squared, which is equal to 1/2 times 1/2 big M r squared over v squared or r squared, canceling out my r's. That equals 1/4 mv squared. Plugging in 1/4, and sorry, that is big M. Plugging in, I get 1, and the velocity I calculated earlier. Okay, and the rotational kinetic energy gives me 5.88 joules of energy here. The initial gravitational potential energy is mgh, which is 2 times 9.8 times 1.5. So my initial gravitational potential energy is 29.4 joules. So our percentage here is EKR over unity times 100% equals 20%. So 20% of the gravitational potential energy has been transformed into rotational kinetic energy. The other 80% has likely mostly gone into the kinetic energy, and some of it could have been lost to friction or heat or anything like that. In the ideal world, we're told to ignore air resistance and friction at the axle. So assuming that this is perfect, this calculation, then 20% of the energy will be transformed to rotational kinetic energy, and 80% will go to translational kinetic energy of the block. So that was question 4. Question 5. A uniform disk with radius 0.25 meters and a moment of inertia of 0.15 kilogram meter squared is initially at rest. A small projectile of mass 0.05 kilograms travels at a speed of 30 meters per second and strikes the edge of the disk at radius and sticks. Assume the collision is instantaneous and there is no external torque about the disk's axis during the impact. Find the angular momentum of the projectile about the disk axis just before impact. So this is just before impact, so I will call this Li for initial angular momentum. One of my equations says that it's equal to mvr, and plugging in the values, I get 0.05 times 30 times 0.25, and that is going to give me 0.375 kilogram meter squared per second. So that is my angular momentum, of the projectile about the disk just before impact. B, find the common angular speed of the disk and projectile immediately after the collision. The moment of inertia of the projectile when attached to the disk is mr squared. So I know that initial angular momentum has to equal final angular momentum, and that is going to be, the final angular momentum is going to be the angular momentum of the disk. I'll use a D, which is I omega, F plus mr squared omega F, and this here is the I of the projectile. So I'm told that the moment of inertia of the projectile is mr squared. I've just subbed that in right away. So continuing on, initial angular momentum is going to be equal to omega F, if I factor that out, times the I of the disk, the moment of inertia of the disk, plus mr squared, and rearranging for omega F, I get the initial angular velocity over the moment of inertia of the disk plus mr squared, and this will be 0.375 over 0.15 plus 0.05 times 0.25 squared, and that gives me a final angular velocity of 2.44898 radians per second. Lastly here, part C, compute the rotational kinetic energy after the collision and compare it to the initial kinetic energy of the projectile. What percentage of energy is lost in the inelastic collision? So first, I'm going to find the rotational kinetic energy after the collision here. that is 1/2 I omega squared, which is equal to 1/2. And here I'm going to add both of the moments of inertia together. Pretty much exactly as how we did it earlier. And we just found omega F. So this is the 2.44898 squared that we just found in the previous part. And this gives me a final rotational kinetic energy of 0.4592 joules. The initial kinetic energy, EKI, is equal to 1/2 mv squared. So that is 1/2 0.05 times 30 squared. So the initial kinetic energy is equal to 22.5 joules. Putting this all together, my percent loss formula that I will build myself is 100 minus EKRF over EKI, what I just calculated, multiplied by 100%. And that is going to give me about 98%. So 98% of the kinetic energy I is lost. Only a little bit of it makes it to the end there. So that was assignment 11. If you have any questions, please ask me in class or email me. Thank you.